And here we are once again. Physics 105B, video lecture 8. So we're deep into the Lagrangian mechanics at this point. And we did symmetries and conservation laws, we built up the formalism. So we're going to start solving some problems. Our next big goal is the theory of small oscillations. And yeah, that's going to take a little bit of doing. It's a great theory. So first of all, Lagrangian mechanics. In fact, this is one of those theories, small oscillations with many degrees of freedom. We need Lagrangian mechanics for that. Okay. And we'll see why. It's a perfect application. So, small oscillations of systems with many variables. So now instead of just 1 degree of freedom with systems with many degrees of freedom, but we will start with 1 degree of freedom. We'll do a quick review of what we know about small oscillations. So small oscillations, here's what we're going to do. We begin with a system of this form, and since we're in many degrees of freedom, I've got ij, aij of q, qi dot, qj dot minus dot there, u of q, and coordinates. And we want to tackle that for n degrees of freedom, but we're going to start with 1 degree of freedom for 1 degree of freedom. What does this Lagrangian look like? L is equal to 1/2 A of Q, Q dot squared minus U of Q. So that's a little more general than our 1/2 M V squared, right? 1/2 MV squared minus U. So I'm going to give an example of a system with 1 degree of freedom that looks like this. In fact, I could give 2 examples pretty quickly. Okay, yeah. Here's our example. What we imagine is that we are on a frictionless curve, so we're a bead on a frictionless wire, or a car on a frictionless track, and the track is y of equals f of x. There's our x-axis, there's our y-axis. So yeah, this is one of those examples where we are in 2 space, but we have 1 degree of freedom because we can just move along the curve. So how do we construct the Lagrangian for this? L is equal to, didn't draw my particle, huh? M, there we go. So L is equal to 1/2 mv squared. X dot squared plus y dot squared. Actually, let's not call that L yet. This is just the kinetic energy. The potential energy is mgy. But that's not yet a Lagrangian. We have y equals f of x. Y dot is equal to f prime of x, x dot. Okay. And now when we build this in, we're only going to have the x here. So we have t is equal to 1/2 m x dot squared plus f prime of x squared x dot squared. U is equal to minus mg f of x. So now we have the ingredients. Okay. we'll go ahead and here. Now we're going to have L equals 1/2 m1 plus f prime of x squared x dot squared minus mg f of x. So now we have a Lagrangian and you'll notice, to complete this thought up here, this is my A of Q. I'll put a bracket around it. See, so it's 1 degree of freedom, but it's 1/2 function of the coordinate, which is what that means there, times the velocity squared. So there's our Lagrangian. Let's move this down. Okay. There's our Lagrangian. And it's an example of what I was going to say. Now, where would the small oscillations come into play? The small oscillations would be around this local minimum. So I could say x0, small oscillations about the local minimum at x0. Okay. It's going to roll around in that trough. So that's enough of an example. I may leave this as an assignment because the example set up really nicely, but let's go ahead and continue on with the analysis of this Lagrangian, this having been an example of it that we could assign at any time and you'll keep running with. Now, so the situation is this. For the small oscillations, so I'll call this next small oscillations Lagrangian. What we do is we expand U of Q, no, not U of Q, expand A of Q for starters. Actually, let's start with expand U of Q equals U of Q0 plus U prime of Q0 times Q minus Q0. It's not an X, that's a Q. Q minus Q0. You guys remember this, of course, plus 1/2 second derivative Q minus Q0 squared plus and so on. And this is a constant. We know we can add and subtract constants from the Lagrangian at will, just like with Newton's laws. This we're going to say is 0 because we're expanding about a local minimum. And this is the next term that's left, and the higher ones are negligible. So we went through this last semester, all the conditions on this thing, that it exists and be positive. So we'll just cut to the chase, and our new potential energy, or the potential energy that we're then interested in, is U of Q 1/2 U double prime minus Q0 squared. Now this time we're in this world here, this object, we're going to expand A of Q as well. I'll just erase this side for now. Okay, we're going to expand A of Q. So we're continuing down here. Expand U of Q. Expand A of Q equals A of Q0 plus A prime of Q0, Q minus Q0, plus and so on. Okay, so A of Q we don't expand to second order. The reason is this: we're trying to get a small oscillations version of this Lagrangian. We already know what's going to happen here, quadratic approximation. The A of Q times Q dot, the point is we can keep, by making this small, we can keep A of Q as close to A of Q sub 0 as we want, which means we're just going to end up with a constant. So as before, small means small enough. And now our A of Q is simply replaced with A of Q0. So what I call the small oscillations Lagrangian, L sub SO, is equal to 1/2 A of Q0 Q dot squared, right, minus 1/2 U double prime of Q0 Q minus Q0 squared. And having come this far, we're actually going to this wasn't the real one yet, okay? In terms of the nomenclature, 1/2, so our A of Q0, which is just a constant from this function here, is going to be just named M. Even though it's not the mass, we're just going to name it M. The Q minus Q sub 0 we're going to name X, so we'll have 1/2 M X dot squared minus 1/2 K X squared. Yeah, this is the one we would have just written down anyway for the harmonic oscillator, but now you see where it came from. Okay, this A of Q0, that's what we're calling X, and that's where it came from. And by the way, you can see what's going on here as well. This is the perfect example. This example with the bead. And the U double prime of Q sub 0 is the K, and Q minus Q sub 0, X is equal to Q minus Q sub 0, so of course X dot is equal to Q dot. So yeah, and once you have this, then you should look at this and say, yeah, I know what happens next, okay? Newton's law, or the Lagrange equation, is just going to give us Newton's law, Hooke's law for the harmonic oscillator, and then we can just write the answer down. Okay. So that's for 1 degree of freedom. That's what I just wanted to remind you of, this whole process. This example here is really nice. In fact, I'll just point it out while we're on the subject. Of course, we saw the oscillations are clearly going to exist around the minimum. And this A of Q here, which is this thing in the red bracket, the expand, you don't even have to expand, because you see what's going to happen when you have F prime of X0 vanishing because you're the local minimum. You're just ending up with an M. But very important, if you were to take the Euler-Lagrange equations for this object, okay, and try to solve them, it would be a fully nonlinear, difficult to unsolvable type of equation. It's only when you go to the local minimum that things become so easy, and it's just a classic small oscillations problem. So I'll just add a couple of these things here, kind of small, but you guys don't want to shortchange yourself on this. So next, Euler-Lagrange equations. dl dx dot is mx dot, time derivative of that is mx double dot, and then cancel the 2 and d dx, you're going to get minus kx, or plus kx equals 0. which is of course the well-known. Here, I'm just going to sneak it in here. Weird, send everything up. And then what? X of t is equal to a cos omega t plus alpha, or whatever you want to call that phase. Omega equals root k over n. Okay, that's everything we inherited from last semester when we studied this. So really, once you see this form, you know what's going on. Okay, once you see this form, kinetic minus potential, and that's the small oscillations around a local equilibrium. Good. So now what we have to do is generalize this to the n-dimensional case, which isn't up on the board anymore. You have to work with the full Lagrangian. The full Lagrangian. So let's go ahead and send this up. This is the time when I spend a fair amount of time on the multivariable calculus Taylor series. Okay. Experience shows that the students don't really know it or love it, although they should. But we're here to review that. So I'm going to rewrite the Lagrangian, and we can actually even see what's going on there. But then we'll talk about multivariable Taylor expansions, because we're going to need them a few times this semester. And this is the time to really study it, understand it. There's a way to make it really simple, and you'll be surprised. Okay, back to many degrees of freedom. Because I can already point out some of the things that are going to happen. So we have 1/2 double sum Ai j of q, qi dot qj dot u of q1 to qn. Write them all out, I and j. So this is a mechanical system, and we're going to look at it near equilibrium again. Now we already had a couple of, we have one or two or more, but we did have a perfect example of that system, so I'll remind you of it. That was the mass on the track with the pendulum hanging from it, and it was attached with a spring. Okay, that was a perfect example of 2 degrees of freedom and horrible Lagrangian, or very complicated Lagrangian, but it will simplify substantially when we go to the near equilibrium position, or we go to the equilibrium position. In particular, you can see what we're going to have to do compared to what we just did. We're going to argue that we can evaluate these coefficients at the equilibrium, just like we did above, and we're going to expand this thing in a Taylor series to quadratic order about the equilibrium position. So for this system, whose example we have in our notes, whose Lagrangian we have, evaluate Aij at equilibrium, and so expand. So that expansion we do with Aij means we just have to evaluate these things. We don't have to do anything to them. We just plug in a value. Expand u of q to second order the way we always do. 2 seconds. Second order. Okay. Yeah, this theory is really great, actually. It's going to unfold, and we're going to make it look this simple, even though it won't actually be that simple. We're going to make it look that simple. So we need, so next, the multivariable Taylor expansion. Now, a textbook is just going to assume that you know the multivariable Taylor expansion. But experience shows me that people don't just know it. So I'm going to derive it and generate it for you. Give us a chance to talk a little mathematics, and then we will return to this problem here. Okay. So this is an excursion into multivariable Taylor expansion. And we will, we'll just start with vectors. So we want to expand f of x equals f of x1 to xn in a Taylor series about some point. In a Taylor series. About x0. So we have n, n variables here. Let's get a picture to, well, first, what we can do is let x equal x0 plus x minus x0. That's a way to look at it. I'll show you what I mean. That's, of course, just a trivial identity, but we're thinking of that's the location that interests us. We need a vector here. This is the location that interests us, and this is the small difference vector that we're going to expand. What this is going to do, it's going to generate a little bit of bookkeeping. A little bit of bookkeeping and indices, but nothing bad. So yeah, the picture that goes with that is we have x0 we have x, and then we have this x minus x0. So in that sense, that would be our small quantity. Okay. So here we go. We have f of x plus x minus x0 and I'm going to write this out so you see what's going on here. We have x1 plus this is an x0 here. Let's write out all of the variables here. So we get an x0, 1 plus x1 minus x0, 1, comma, x0, 2 plus x2 minus x0, 2, and all the way out. And if this could be a function, x could be r, this could be in 3 space, of course. So that's what my vector shows. I have a position here in 3 space, and then I have a little difference vector. But here's what we're going to do. Now define g. See, this is a scalar function of a vector variable. So we're going to find g of to find g of t equals f of x0 plus t times x minus x0. And now we have a scalar function of one variable. What is this thing? This time, I need a better picture here to make my point. Okay. Let's do this. This one's easier to. So let's call this x0, this x, and this is x minus x0. Okay, this little difference vector here. And yeah, this is a picture that makes sense. Now if I have t times x minus x0 for t positive, I've got that half line going in that direction, and for t negative, I have that right there. So what this actually, g of t defines is based on this little vector pointing whichever way, you have a line through n space or a line through 3 space. And this t would multiply, from our original example, would multiply this here and this here. So I'm just going to put this here in red. It's not part of the original, okay? Just to show how that goes. For example, this function could be the temperature in this room, and I would just have some x0 as this point at the end of the ruler, and then my x minus x0 times t would be that line that extends across the room, and the temperature here at this point, and then there's a scalar function temperature. You know, maybe there's cool air coming down, warmer at the bottom, vice versa. Warmer at the top, cooler at the bottom. Okay. So now I've defined this. I have a function of one variable, and we're going to expand g of t. And expand g of t in a Taylor series about t equals 0, which means we're expanding that line here, that function, right around x0 in a Taylor series. The values of this thing along this line here in a Taylor series. So now the chain rule comes into play. That's why I wrote everything, you know, I wrote a bunch of different explicit expressions down, okay? So g of t, g prime of t is equal to, we get a sum, partial f, partial x sub I, okay, and we'll just take one of them. Partial f, partial x sub 1, that's the initial slot, and then the derivative with respect to time gives us the x1 minus x01. So this of the arguments, and then the chain rule gives us x sub I minus x0 sub I. And should I write this argument in here? I'm just going to write of x. So that's g prime as a function of t. That was a chain rule, best seen right here with the t in place, or seen down here as that one coordinate. And since I'm going to evaluate at t equals 0, then it'll just be df dx of I evaluated at x0 if I evaluate that at t equals 0. So that's what I'll get. Okay. Now the second one, and we're only going to need 2 of these, by the way, so it could get hairy, but the second one, g double prime of t, what we do is we just imagine this whole thing is simply a function of these arguments. Okay? These are all constants because of t. It's a function of these arguments. Again, we could give it a new name. Function of these arguments, and the t only shows up there and there, right there. So the second derivative, you can put parentheses around this thing, you would have sum over j equals 1 to n. In fact, I will put parentheses around this thing. df dxi of the arguments xi minus x0i. So what's in these parentheses here is these arguments again. Okay. Let's put a star there. And because of that, the rest of the chain rule is going to do this. D squared dxj dxi. And then the inner derivative is going to bring down what we had before with a different subscript. So xj minus x0j. And if we evaluate at t equals 0, here, let's try this with some colors. Evaluate this at t equals 0, then we're going to evaluate that at x0 again. Okay. And once you see this pattern and you see we're just doing the chain rule again and again, then you can see what would happen with the third derivative. We'd have a third, oh, I missed the sum in here. Not so good. Let me make this a little nicer. There was the original sum here, dxj dxi, j and I. Right. This whole thing was supposed to go in these parentheses here, like that. It is possible to make this a little cleaner. You know what? You guys have this in your notes anyway. Let me express it this way. I would have had that sum d dx j, and now I have this d f dx I of the argument up there, xi minus xi0, close parentheses, xj minus xj0. And when you evaluate it at t equals 0, then you put in evaluated at x sub 0. And now you can see how the argument would go. If I had a third derivative, I'd have a third sum, I'd have third derivatives, and so forth and so on. You could just generate it with a machine at this point. Okay. So here's what we have. G of t is equal to g of 0 plus g prime of 0 times t plus g double prime of 0 over 2 t squared and so on. And we're just going to take that, put these things in, and we will actually have our Taylor expansion. we'll have our Taylor expansion along this red line, but these guys are arbitrary, and suddenly we have it in all space. So let's see, I gotta erase all this stuff now. G of t is equal to this, and G of t equals 1 is equal to f of x. Of course, I just erased that, but you have it in the board. G of t equals 1 is literally just f of x by construction. So here's what we're going to have. Equals f of g of 0, that's going to be f of x 0. And we're going to have plus sum over df dx of I, evaluated at x0, x of I minus xi0, I equals 1 to n. And for that third term, got the double sum, and got the 1/2 right here. See, when I plug in t equals 1, of course, this just turns into 1 and a 1. I'm going to have 1/2 double sum ij d squared f dxi dxj of x0 xi minus xi0, running out of room, xj minus xj0. And any higher terms you could write down, but you wouldn't want to, because you'd have a triple sum and so forth. So I'm going to rewrite this again just so that it's neat enough and you see the construction principle. So again, and right underneath this, I'm leaving room, right underneath this I'm going to put the one-dimensional Taylor series, and we'll see how these are related. So we have f of x equals f of x0, and then we have the sum I equals 1 to n, and this just comes from the chain rule, df dxi x0 xi minus xi0 plus j d squared f dxi dxj. Hope this is a little neater than what's above. Okay, I think it is. Xj minus xj0. That's neater, good, I'll erase this one here. Okay, here we have it. We have f of x, the 0th order constant term, the linear term, the quadratic term. These go from I and j, go from 1 to n. And what I want to show you is that this is just bookkeeping. And it's constructed in such a way that you can do it very mechanically. Okay? But first of all, if n is equal to 1, what do we have? We have f of x 0. If n is equal to 1, this is just one first derivative plus f prime of x0, x minus x0. Right, and so far, this is, remember, when we talked about this last semester, we were saying this is just the equation of a straight line, okay? And then we would have plus 1/2 f double prime of x0, x minus x0 squared. So this is really important to realize, because in these complicated mathematical formulas, in our mind's eye, we want to see this one. This one is so clear to us. Point, straight line, quadratic, so, parabola and so forth, right? This one is very simple. And we know, for example, if we have a vanishing first derivative, then we have either a local minimum or maximum. Okay? Now, in the n variables, this is just the sum 1 to n of these first derivatives times these linear difference. And here's double sum second derivatives, and these are then the quadratic terms. So you can get used to this. What other point do we have? Important points to make. Here's another way to look at this. This could be thought of as a dot product between an n-dimensional gradient and a vector. So this here, I'm going to put gradient f dotted into x minus x0. That's what this means. In 3 dimensions, literally, in n dimensions, as a scalar product with the sum there. So now we come to this term here. This is a quadratic form. I think we'd already mentioned that in terms of the kinetic energy. So we have to become accustomed to these types of expressions as well. The double sum. And the principle of the bookkeeping is pretty easy because you're summing from 1 to n, 1 to n. So if you're writing these out mechanically, you have f11, right? Second derivative, you have f11, and then these things. Then you have plus the f12 term plus the f13 and so forth, multiplied by those. Maybe I could write that a little different. So, but you'd be going through, you'd be doing an array, 1, 1, 1, 2, 1, 3, 1, 4, and then your next row, you'd be the 2, 1 term, the 2, 2, the 2, 3, the 2, 4. And if you have more, the 3, 1, 3, 2, 3, 3, 3, 4. Here, let's actually leave this up. And you'd just be summing all of these. The 1, 1 term, the 1, 2 term, the 1, 3, plus, all the way through. And with a 2 by 2 matrix, it's not such a big deal, is it? Okay, so we have the quadratic form here, and we have a linear term here, and a constant. And this is our simple Taylor expansion. So I'm going to have to do a little more characterization of this expression, but this one's pretty clean. I'm going to leave it up. And the construction, if we put any notes here at all, just write chain rule, multivariable chain rule. I'll put that for you. Variable chain rule. How we're doing time-wise. This subject always just requires a certain amount of time. We've pretty much run out of time for today. And for now, I would just recommend that you guys work on this, make this as clear to yourself as you can, and then you've got this Taylor expansion. I'm going to come back and spend some more time with this. We have to characterize local minima and local maxima and things like that. It turns out that this array, this n by n array of second derivatives, gives us our maximum minimum criteria. Okay, so this matrix, if you want to call it that, generalizes your one number, which is your second derivative. Yeah, one important point to finish with. These are, of course, all constants. That's the meaning of an expansion. you evaluate those derivatives, so they're all constants. Same with the gradient, those are constants, those are constants. Okay, that's enough for now. You guys go ahead and try to understand this and straighten it out in your mind. It's a great subject. Okay, see you guys next time.